In this video, I'm going to go through AQA AS-Chemistry paper from 2017, and this is paper 2. I'm going to do the first half of this paper in this video and the second half in another one. Okay, so the first question is about the Maxwell-Boltzmann curve. Label the horizontal axis. Well, that should be energy. Okay, the energy that the particles have. Sketch a distribution of molecular energies for the sample of a gas at a higher temperature. Right, so at a higher temperature, we've got to make sure we, so this peak has got to shift that way because the average energy of the molecules is going to increase, but we've also got to make sure that that peak is lower, and the reason for that is the area under the peak is proportional to the number of molecules and the total number of molecules, and that's not changing. So you've got to, for the 2 marks there, you've got to have the peak shifting to the right, and it's also got to be lower. Okay. This gas decomposes on heating. Explain why an increase in temperature increases the rate at which this gas decomposes. Okay. Well, there'll be a certain amount of energy, a minimum amount of energy that the gas molecules will need in order to decompose, and we'll call that the activation energy, EA. And you can see at a higher temperature, or at the lower temperature, you've just got that area under the curve there. It's all those molecules that can decompose. At the higher temperature, the area is now that blue area, which is a great proportion of the molecules. So more molecules have the necessary energy, the minimum amount of energy, the activation energy, in order to react. Okay, this is an ideal gas calculation. So an experiment was carried out to determine the MR of a hydrocarbon that is a liquid at room temperature. They heat it up, and the stuff vaporizes, and then you measure the volume of the vapor using a gas syringe, and you can work out the number of moles. So the 2 equations we're going to use for 2.1, we're going to use PV is equal to nRT, where n is the number of moles, and we're also going to use moles is equal to mass over MR. So that's n. Okay, so we're going to find out n, and then we're going to substitute it using the ideal gas equation, and then substitute that value into here to work out the MR of the gas. So let's rearrange the ideal gas equation. So we get n is equal to PV divided by RT. Always got to be really careful with the units in the ideal gas equation. So P is 102 kilopascals, but we've got to put it into pascals, 102,000. V is 72 centimeters, but we have to convert that into meters cubed. There are 1 million meters cubed in a centimeter cubed, so that's equal to 72 times 10 to the minus 6 meters cubed. Put that in there. R is 8.31 joules per mole per Kelvin, and the temperature is already in Kelvin for us. That's 373. So put those, work out that, and we get a value of 2.37 times 10 to the minus 3 moles. Now we have to put that value into this equation up here. We're told the mass of X is 194 milligrams. That's equal to 0.194 grams divided by 1,000. So let's rearrange that to get MR. So MR is equal to mass divided by moles. So we've got 0.194 divided by 2.37 times 10 to the minus 3 gives us a value of 81.8. Now, significant figures. We should give it to 2 significant figures because look, the volume is only given to 2 significant figures, so we shouldn't give it to 3. So our answer should be 82. You always give your answer to the number of significant figures, the least accurate bit of data, which in this case is the volume, because that's only given to 2. Okay, right. Analysis of a different hydrocarbon Y shows it contains 83.7 by mass of carbon. Calculate its empirical formula. Well, if it's a hydrocarbon, it's only got carbon and hydrogen in it. So in 100 grams, we would have 83.7 grams of carbon, and we would have 100 minus that, so that is 16.3 grams of hydrogen. Okay, we need to convert that into moles, so that's equal to mass over atomic mass, AR. So that's 83.7 over 12 and 16.3 over 1. That's our molar ratio. That works out to be 6.975. That's obviously 16.3. Simplify our ratio by dividing by the smallest number, which is 6.975. So we've got there 6.975 over 6.975. 16.3 over 6.975. That is equal to, obviously that gives us 1, and that gives us 2.33. Now we need to get whole numbers, so we multiply that by 3. We are going to get whole numbers, so that means the ratio is going to be, running out of space there, so it's 3. 3 times that gives you 7. Okay, so the empirical formula is, that's the simplest ratio, is C3H7. Now, you know you can't have a compound of that formula because there's a wrong number of hydrogens to carbons. And it also tells us that the MR is 86. Well, if you multiply that by 2, you would get to, it's going to be a multiple of that, 2 or 3. Multiply it by 2, you get C6H14, and the MR of that is equal to 86. So the molecular formula is C6H14. So it's a saturated hydrocarbon. Okay. Right. So compounds A, B, and C all have the molecular formula C5H10. Right. So let's look at that. We've got to work out what these are. C5H10. Well, you can tell it's not. It doesn't fit into that formula. It's not CnH2n plus 2. It's just CnH2n. So that means there must be one double bond, or it could be cyclic. Okay. Okay, cyclic alkanes, which are saturated, have that formula CnH2n. A and B decolorize bromine water, but C doesn't. Okay, so let's suggest the formula C doesn't decolorize bromine water. There's no double bond there. So C has got to be cyclic, so it could be cyclopentane. That is a reasonable suggestion. Or it could be, you could have methyl cyclobutane. Either one of those would be fine. B and A do decolorize bromine water. So A and B are alkanes. They've got a double bond in them because that's a test for a double bond. Right. It says B exists as 2 stereoisomers, but A doesn't. Let's do A first. Okay. So we've got a double bond in there. And A doesn't exist as 2 stereoisomers. So that means you've got to have 2 groups on one of the carbons that are the same. So let's try 2 hydrogens. We'll try that. And we've got 3 of the carbons to think about. So we could have CH2, CH2, CH3. Okay. Now that compound does not show EZ isomerism because you've got 2 hydrogens, 2 groups the same. So that could be A, or another possibility for A. You only got to give one, but might as well just, right. It's saying if we had 2 methyl groups on the end there, okay, then that, because you've got 2 groups on the carbon, that can't show stereoisomerism. And how many carbons we got left? We've got 1, 2, we've got 4 there. We need one more. So A could be that as well. Okay. Now B does show stereoisomerism. So all we've got to do is draw the double bond here, and let's do B. We've got to make sure that it does have 2 separate groups. So right, let's keep it as simple as possible. We can have an H on one and a CH3 on the as the other group there. Now we've got 2 other carbons to worry about, so we could have CH3 there. Now we can't have a CH3 there because then so we've really got to have, that's got to be CH2. That's got to be an ethyl group there. So that, I think that is the only thing that B can be. There's no other possibilities for B. There's a few things possible for A. Right, now state the meaning of the term stereoisomers. So stereoisomers is well worth learning. The definition is same structural formula, different arrangement of atoms in space. That's a good definition of a stereoisomer. Right, how do they arise in compound B? Well, it's because you do not get rotation, again, around a double bond, just because there's a pi bond there. And also, you've got to say you've got to have 2 separate, two different groups attached to the carbon with a double bond. And there's 2 carbons there with double, obviously in the double bond, and each one has got to have 2 different groups attached in order to give rise to stereoisomerism. Okay, so that should cover all the marks in that question. Right, question 4. Alkanes are burned in excess of oxygen. They produce CO2 and water. Write an equation to show the complete combustion of propane. Right, propane is 3 carbons, C3H8. It's saturated, so 2N plus 2 plus oxygen. That's going to give us CO2 and water. We've got 3 carbons on the left, so we need 3 CO2s. We've got 8 hydrogens on the left, so we're going to need 4 waters. That means we have used up, on the right-hand side, we have got 10 oxygen atoms, so we need to put a 5 in front of the O2. So that is the equation. Right, 4.2, an expression can be derived using bond enthalpy data to estimate the enthalpy of combustion, delta HC, of an alkane. For an alkane with N carbons, it's given by this formula here. The enthalpy of combustion of an alkane was shown to be that, so use this formula to work out the molecular formula of the alkane. Right, so we've got to put the numbers in there. So delta H, they tell us, is minus 665, so that's minus 6650 is equal to minus 496N plus 202. Right, let's get rid of those brackets. So that's going to become minus and minus 202. Take the 202 to the other side, so we got minus 6650 plus 202 is equal to minus 496N. We get that's going to be minus 6448 is equal to minus 496N. Divide through by 496, we get N is equal to 13. Okay, so we've got 13 carbon atoms, and alkanes are always CnH2n plus 2, so that's C13H28. Suggest one reason, other than the use of mean bond enthalpies, why a value for the enthalpy of combustion of a liquid alkane is different from the value obtained using the expression. Okay, right. Now, I think what they're looking for here is it's a liquid alkane, and it said in the previous expression this was for it doesn't say it's a gaseous alkane, but I think that's what they're getting at. Okay, so a liquid alkane, you need some energy to vaporize the liquid. So that means you're going to get slightly less energy out from the enthalpy of combustion than you might expect. Okay, values of the enthalpy change of combustion of 1 gram of some alkanes are shown in table 2, and you've got to plot those against the number of carbon atoms, then draw a line of best fit to fill in this value here. Okay, so let's have I've plotted the graph already. The red dots are the points. You can see that it is not a straight line, it's definitely a curve. I've drawn the green curve, and then you've just got to read off the value. Here's 3 carbons for propane. Propane's got 3 carbons, that blue dot is, and that gives about 50 minus 50.8 kilojoules per mole. So that is the value that we should put in the table, minus 50.8 kilojoules there, in that place there. Okay, 4.5. Isooctane is an important component of petrol used in cars. When it's burned, the enthalpy change is minus 47.8. Isooctane is a liquid, okay, right, that's kilojoules per gram, not per mole. Okay, isooctane has got a density of that. Calculate the heat energy released when you burn 1 dm cubed of isooctane. Right, so we need to work out the mass of isooctane. Mass is equal to density times volume. The density is 0.692 gram per centimeter cubed. We've got 1 dm cubed, that's 1,000 centimeters cubed, so times by 1,000, that's the volume, 692 grams. Okay, now it tells us here that 1 gram gives us 47.8 kilojoules out. Okay, so how much is 692 grams going to give us? The energy is going to be equal to 692 multiplied by the energy out, which is 47.8 kilojoules. That gives us a value of, right, that gives us a value of 3.31 times 10 to the 4 kilojoules. I'll leave it in standard form, that's fine. Should we give it to 3 significant figures? That's a 3 sig figs. Yes, we should, because all the data is given to 3 significant figures. So that's our answer there. Okay, so a titration question here, I think. Ethane dioic acid is a diprotic acid. A student carried out a titration with sodium hydroxide to determine the mass of acid in the solution. The student repeated until he got concordant titers. Right, so you got 25 centimeters cubed of ethane dioic acid. It reacted with this much sodium hydroxide. So let's work out the moles of sodium hydroxide. Moles NaOH is equal to the concentration times the volume. Concentration is 0.5. The volume is 25.3 over 1,000 dm cubed. That is equal to 0.01265 moles of NaOH. Now look at the equation. The molar ratio is 1 to 2. So the moles of ethane dioic acid are C2. Moles of ethane dioic acid. Well, that's going to be equal to 0.01265 divided by 2, which is equal to 6.325 times 10 to the minus 3. Right. Now, that's the number of moles. Calculate the mass in 25. Well, that's the moles in 25. So to work out the mass, we've just got to multiply by the MR. Right, the MR of H2C2O4, that's equal to 90. So the mass is equal to the moles times by the MR. 6.325 times 10 to the minus 3 multiplied by 90 gives us 0.56925 grams. Right, and it asks us in milligrams, so we've got to divide that, multiply it by 1,000, and then think about significant figures. Well, we're going to give it to 3 significant figures. Everything, all the data is given to 3 sig figs, so that's going to give us 569 milligrams. That is our answer. Right. The student used a wash bottle containing deionized water when approaching the endpoint to rinse the inside of the conical flask. Why does this improve the accuracy of the titration? Well, if you've got your conical flask here and you've got the burette just above it, sometimes you get little splashes of liquid from the burette getting stuck on the side of the conical flask when it should all be going in there. Okay, and so these bits of acid are not going to be reacting, so you'd end up adding more acid than you really should do. But if you wash with distilled water, you'll remove them, and then you'll get a better, a more accurate value, closer to the true value, because you won't end up with any acid stuck to the sides. Concordant titers, what does that mean? It means in agreement with each other, and that's usually taken to be within 0.1 centimeter cubed of each other. Right. 2-methyl-propane-1-ol can be prepared by reacting 1-bromo-2-methyl-propane with dilute aqueous sodium hydroxide. Name and outline a mechanism for this reaction. Well, let's first draw the starting material, and that will do the mechanism. 1-bromo-2-methyl-propane. So we want 3 carbons in a row with a CH3 on carbon number 2 and a Br on carbon number 1. So that is our, let's write this one as a CH3. Okay, now the mechanism for this is going to be, of course, nucleophilic substitution. The nucleophile is the hydroxide ion. Okay, the sodium, of course, is just a spectator ion, doesn't do anything, so that definitely doesn't appear in the mechanism. Right, we have a delta positive, partial positive charge on that carbon due to the electronegative bromine. The pair of electrons, that lone pair forms a bond to that carbon, and then the pair of electrons in this bond go onto the bromine. And we'll draw the product there. We're going to get CH2OH. That's the mechanism. Right. When 20 centimeters cubed of 1-bromo-2-methyl propane will react with an excess of sodium hydroxide, 895 milligrams of the alcohol were formed. We've got to work out the percentage yield there. Okay, right. So we have to remember that 1 mole of haloalkane is going to give us 1 mole of alcohol. It's a 1-to-1 ratio. Right, what is the mass of haloalkane to start off with? So mass, well, they give us the density, and they give us the volume, 2 centimeters cubed. So the mass is going to be equal to, of the haloalkane, is going to be volume times density. That is equal, the volume is 2, the density is 1.26, that is equal to 2.52 grams. Right, now we need to work out the number of moles of the haloalkane. That's equal to the mass over the MR, and they give us the MR. They say, what is it? 136.9. So 2.52 divided by 136.9 gives us 0.0184 moles. Now, 1 mole of the haloalkane gives us 1 mole of the alcohol. So therefore, the moles of alcohol are going to be, that we get if we've got 100% yield, would be equal to that, 0.184. So the mass of the alcohol is equal to the moles times by the MR. So that's 0.0184 multiplied by the MR of the alcohol, tells us is 74. That is equal to 1.362 grams. So that's if we get a, that's what the expected yield. Okay. Now, they didn't, how much did they get? They got 895 milligrams. Okay, so percentage yield is actual over expected multiplied by 100. The actual yield was 800, so that's equal to 0.895 grams. So 0.895 divided by the expected amount, 1.362, multiplied by 100. That gives us 65.7% yield. Okay. (6.3) Okay. When 1-bromo-2-methyl-propane reacts with hot concentrated ethanolic potassium hydroxide rather than the aqueous sodium hydroxide, you get a different product. What do you get? Well, you get elimination to produce an alkene. So name the organic product and name the mechanism for this reaction. So it's just elimination is the name. We don't have to outline the mechanism, but just name it. Right, let's draw the starting material, which is 1-bromo-2-methyl-propane. So got a CH3 there. We've got a bromine on the first carbon. Right, now in elimination, you remove the halogen atom and a hydrogen from a carbon next door. We've only got one carbon next door, this one here. So we'll remove that hydrogen. So we're going to end up with a double bond there. So if I just rub that out now. So that is the product we're going to get. Okay, name this organic product. Well, what is it? It is 1, 2, 3. So it's propene. But we have a methyl group on the second carbon. We don't really need to say 2-methyl because it can only be on number 2. And so we just call it methyl propene. I think they'd let you get away with calling that 2-methyl propene, but you don't really need the 2. Okay. And that is as far as I'm going to go with that particular paper. I'm going to do the next half in the next video.